Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 14's assignment, Categorical Contingency Tables. So typically they're called either categorical tables or contingency tables. I'm calling them both so that you're introduced to both of those terms. So we'll scroll down to Class 14 in the timetable, and we have a couple files to download. This is a separate assignment. It is not part of your all project. So we'll download the two files, the R Markdown file, and we'll put that into the classwork folder. And we'll also download the associated data file and put that in the same folder. There's also a link here to Simpson's paradox. This link actually goes back in time to 2014. It actually is on the web archive.org site, because unfortunately this wonderful page went away. But this page, I encourage you to play with this a bit. Read through this and understand what Simpson's paradox is, and you can use some of these cool sliders and switches to try to understand how Simpson's paradox works with both categorical data as well as continuous data. For example, down here it says we're currently not in the Simpson's paradox, but if you increase the mens up here, then we are in a situation of Simpson's paradox. So do spend a little bit of time with that. All right, let's go back to our assignment. We'll go over to RStudio and open up. Need to switch to the classwork directory and open up that RMD file. And first thing we can do is just knit this file. I know, however, also that I'll want to set the working directory to the source file location. Okay, so that happened in the console, but Markdown is still running over here. When this finishes, we'll open this file in the browser and we'll walk through it. All right, so let's start at the rubric. Answer the questions in this document, compile it to HTML, print to PDF, and submit it to UNM Learn. Do not add this to your all project file. All right, we have two examples to look at today. Something about admissions rate, one example with admissions rate, and the other about death penalty. All right, so for admissions, first we load the tidyverse in. We're going to read in the data file that we downloaded from the website. It has school majors, and it has three variables in it, all factor variables: gender, acceptance, and school. And there are ways to convert these to factor variables when you read it in, but I'm choosing to do it explicitly here. That's going into the data frame dat_ADM for admissions. All right. And here's the structure of our data frame. Gender, acceptance, and school are these three factor levels. Gender is female and male. Acceptance is that you were either accepted into the program, which is a success, or you were not, a failure. And then there's two schools, art and business. This is a subset from a larger data set. In fact, it's part of the data set that is shown in the Simpson's paradox applet. I think, yeah, the Berkeley College one, where there's these different departments, 6 of them, and when you combine all the departments, it turns out that the acceptance rate, the blues, seems that men are more likely to be accepted to Berkeley than women, but Simpson's paradox here shows that if you look at it within each department, it actually is quite equal, or in some cases the women have a much higher chance of being accepted. Okay, so that is one of the things that we're going to see in this example. Did this get smaller? Admissions, yes it did. Okay, so let's look at the admission rates by gender. So here we're looking, I've made a table. Oh, I guess I've hidden a lot of the code here. Of course, you know where to find it. But I've hidden all the code because this assignment is all about interpreting the results and not writing your own code. But what we have here is we have a table under gender. We have the first two rows are females. And we have failure as the first and success as the second rows. We have the frequencies. So I've counted up how many. And I should remove this, but ignore this option. And then proportion is the out of these two frequencies, right? So if you add these two up, you should get 200. And out of those 200, 56% were not accepted. That's a failure. And 44% had a success, that they were accepted. And that visually is provided in this plot here. Okay, the blues are successes, females on the left, males on the right. So we have about 44% for females and 55% success for males. Okay, seems totally unfair on the face of it. We do note that males, there are many more males who are applying, right? If there were 200 total females, we have 360 or so males. All right. So the first question to answer, and worth 2 points, is to interpret the table and the associated plot. Okay, and I give you an example for language. The proportion of females is, okay, so I guess I would probably add some language here. The proportion of females who are accepted is, and I would scroll up and say female success is 44. Okay, so you can either put 0.44 as a proportion, or if you wanted to write this as a percentage, you could say percentage equals 44%. Okay, which is some percentage or proportion higher or lower than males. Okay, so we look up here and we see that females are 44, males are 55, and so that is 11% or 0.11 lower than males. Okay, so that would be the answer to the first one. Then we see something interesting. Okay, let's look at this for each school. So same analysis, but for each school. So let's see how much we can get on the screen if I make this a little bit smaller. Okay, anyway, on the bottom we have gender. I'm going to scroll up just a little bit. It cuts off the word gender, but we've got everything in the table that we need. Right about, well, almost. Yeah, there we go. So females are on the left. So in art school, that's the first 4 rows here, we have females and then males. And then the next set is for the business school. Okay, females and then males. And here we see successes for females is 80%. That's this blue bar over here. 80% for the art school. And for males, we have 75%. That's this blue bar here. So females are actually accepted more with, a higher acceptance rate for females than for males at art school. What about for business school? Turns out, same thing. Females at business schools get 20%, and then for males, 15%. So that is Simpson's paradox, that when you condition on a variable such as which school you're in, your results change. When we didn't condition on school, it appeared that males had higher acceptance rates of 55 compared to 44, but when we look at each school separately, females have higher acceptance rates. That's the paradox. There's no trick here. This is correct. It has to do with sample sizes and acceptance rates being different. Sample sizes being different between the two genders in this case, and acceptance rates being different between different schools. Okay, so then I ask you to interpret the table and the associated plot. Okay, so you can do something very similar for school art, right? For art school and for business school, you can write similar sentences as what you wrote before. So if you like what you wrote before, copy and paste that down here, and then fill in the school name, and then fill in the proportions. Okay. Compare the acceptance by gender, where schools were combined above, to when schools were treated separately here. And what do you observe? All right, so I've already talked about that. Does it surprise you, and why? Okay, so I want you to state the obvious situation here, which I already discussed, that the males were higher before, but females were higher for each school separately. And what's the name of the paradox? So I don't have you explain the paradox, but please do take a little time to explore this paradox. In practice, so that's the end of this example. This paradox, Simpson's paradox, doesn't come up very often for real data examples, but I am giving you a real data example here, and it comes up enough if you're in my position where you see lots of data sets. It comes up enough that it's worth understanding that this is something that can happen, in particular because you may be in a situation where you're working with someone who can't believe the pattern that they're seeing, and in fact there is an explanation for it, and many examples to show why it happens. All right, the second example here is about the death penalty. So 30 years ago, we've got data that was actually taken 15 years before that in 20 Florida counties that studied the effects of racial characteristics on whether individuals convicted of homicide received the death penalty. Okay, we've got over 300 subjects, and we want to know, is there an association between the death penalty and the defendant's race and the victim's race? And fortunately, our country has moved beyond these types of issues, right? Oh, wait. I'm just hearing now that, in fact, we have not moved beyond these issues. Okay, well, we'll keep working on it. Anyway, so is there an association? What is that association? And let's summarize the data. So we have for our data, let's go back to the data. I'm showing you another way to read data sets in. So instead of having something in a file like a comma separated values file, CSV file, or a tab delimited file or whatever, if you've got a very small data set, this is a handy way of creating a data set. You can use the read table function within the R base functions. You don't have to load a package for this, and you can specify text. Text equals, you open a quote and you end the quote. Okay, you open the quote on a non-data line and you end a quote on a non-data line. You can put in headers, and if you do, you need to specify the option header equals true, and then you put in all of your data. And it will, I think that it uses the default delimiter is spaces. So all these spaces are treated as a delimiter, and so every column gets put into its own column of data. If you use this, be sure not to indent your data. Otherwise, it treats the leading spaces in front as a delimiter, and it starts your data in the second column, which is not what you want. Anyway, so this part reads in the data set, And then I've done a couple things. I've converted it from a data frame to a tibble, which is the tidyverse version of data frames. And then I've factored each of the three columns that have character data, so that white and black, the races of the defendants and the victims, are factor variables, as well as the indication of whether they receive the death penalty, yes or no. And then the frequency column is numeric, and it says how many of these defendants either received the death penalty or did not, based on whether the victim was white or black. Okay. So when we look at the structure of this data set, we've got that defendant, victim, and death are all a factor variable, and frequency is an integer. All right, let's get to the data analysis part. So I've got code here that creates this frequency table. Oh, you know, I should have made this way prettier. Oh well, too late now. It's possible that when you download this, it will be prettier, depending on how ambitious I feel. All right, so we've got defendant. So what I've done is I've looked only at the defendant. Okay, we're not looking at the victim yet. The race, just looking at the race of the defendant. Okay, so the defendant, the person who is convicted of murder, homicide, was either black or white. And let's focus on the yes row. So if the defendant was black and they received the death penalty, that happened in 10% of the time. When the defendant was white, they received the death penalty 11% of the time, or 12. So it actually looks in this case that whites are more likely to receive the death penalty. On its face, for me, honestly, this is a surprising result, but also these are pretty close to each other, right? So anyway, so when we look at a plot of that, we can see that if the defendant is black, that is a slightly lower number than with whites. Okay, so now I want you to interpret this table and the associated plot. So in a similar as the example above, write what you see here. All right, so I'm just going to step through what we see when we condition on the race of the victim. So here victim is now in the first column, and we've got I've got a table here, but let's just focus on the plot. I'll make this a little bigger. Okay, so on the left we have when the victim is black. Okay, so when the defendant, that's the person committed or convicted of committing the homicide, when the defendant was black and their victim was black, we have, well, I guess I want to refer to the actual percentages here. Okay, black and black, yes, that's about 6%. Okay, so 6% of the time, I guess what else, I'll just say sort of black on black violence. 6% of the time got the death penalty. However, if you are a white defendant and your victim was black, no one got the death penalty. And let's just look at the total frequencies there. That did not happen very much, a total of 9 times, but all 9 of those people did not get the death penalty. So still, that's a very small sample. I would say that this is weak evidence of discrimination, but it may still be here. Okay. Now going the other way, what if the victim was white? Okay, so if you were black and the victim was white, you had a higher death penalty than if the defendant was white and your victim was white. And let's go look at those numbers quickly. Victim was white. We need the headers here. Victim was white. If the defendant was black, that was 17.5%. compared to when the defendant was white, which was 12.6. These sample sizes are pretty big, and I would say that this 5% difference is probably evidence of some discrimination there, that black defendants are receiving harsher penalties than white defendants. And that was also true when the victim was black. With only a sample size of 9, I hesitate a little bit to make that same strong conclusion. We will learn shortly, when we start doing hypothesis testing, how to assess this statistically and say whether or not there was a difference. Right now we're just interpreting the tables and the plots, what we see. Okay. So I've already given a lot of discussion here. I want you to interpret the tables and associated plots. That's just like in the first example, part 2, where you conditioned on the schools. And then part 8, here compare the death by defendant, where victim's race were combined. That's the first part of the death penalty example, to when the victim's race were treated separately. That's what we've just been discussing. And what do you observe? Right, so in both of these cases, we actually have a Simpson's paradox again. Blacks have higher death rate than whites, but previously, page up, when it was combined, whites had higher death penalties than blacks. So that is the key takeaway here. All right, so that is the end of my introduction for this assignment. If you've listened this far, I've given you all of the answers, but hopefully, I don't really care about giving you the answers or not. What I do care is that you're thinking about it and engaging with the material. In the next assignment, you will take these ideas and apply them to your project.